Uglies. I had a request from a student, or a student asked me about number 12 on the P-series assignment that I gave you. So I wanted to do that. I also can do any of the other ones that you want. I'm just not going to do a whole bunch of videos if I don't think people need them or even watching them. So if you need to see something, just let me know. I'll be happy to do that for you. All right, so number 12 said, what are all values of P for which the series, that series, diverges? And so it should occur to you, if you get a question like this, you're probably going to be comparing it to some other series. And so since we want this thing to diverge, it makes sense that I'm going to compare it to a series that I know diverges. So let's consider this series one over n, the harmonic series, because I know that it diverges. And so what I can do here is a limit comparison. You remember the limit comparison test says that you do all that limit stuff, and then if you get a positive finite limit, then that means that the two series that you were comparing, that they're doing the same thing. So they're either both converging or both diverging. So here's what I'm going to do. I'm going to say the limit as n approaches infinity of my original stuff over the one I'm comparing it to. So we're just going to multiply that by n over 1, and it's in an absolute value. And so what I want to happen here is I want to get an actual answer. I don't want this to be infinity, in other words. I need a positive finite answer. And so we can clean this up a little bit. The limit as n approaches infinity, n over n to the 2p plus m. And we don't really need the absolute value because everything would be positive here anyway. All right, so regardless of what p is, this is just a rational expression that's inside the absolute value there. And remember, we want this limit to be positive and finite. So just think back to your Math 3 days, or even the beginning of this course, when we were doing these limits as n approaches infinity of these rational expressions. Remember, it's just like the way you would find a horizontal asymptote. And so what we want to happen here is we want basically our horizontal asymptote to be a positive finite number. Let's consider a few things. When you're doing it in Math 3, you're just comparing the degree of the numerator to the degree of the denominator. And so let's just consider a couple of things here. So what if, let's let 2p just equal 1. And the reason I did that is because the degree of my numerator is 1. So if I let 2p equal 1, obviously that would make p equal to 1/2. And then if I actually, did that, then that would just make this, let me write the limit. That would make this the limit as n approaches infinity of n over n plus n, which of course is just n over 2n. And so this would be when the degree of the numerator and the degree of the denominator is the same, it's a coefficient over coefficient thing. And so that limit would equal 1/2. 1/2 is a positive finite number, so that's good. That's one of our solutions. If p is 1/2, this limit is positive and finite. Therefore, our original series diverges because we compared it to a series that we knew diverged. All right, so we know it happens at 1/2. Let's consider some other stuff now. So what if 2p was less than 1? In other words, what if that exponent right there was less than 1? Well, obviously that would mean that p was less than 1/2. But then when you were, doing this stuff again, the limit as n approaches infinity, n over, this would be n raised to some number that's less than 1 plus n. And so if p is less than 1/2, making that exponent right there less than 1, Well, then if you're comparing the degree of the numerator to the degree of the denominator, that no longer becomes the term that you determine the degree of the denominator from. It would be that one. And so it would still just be n over n. You know, and in this case, it would be 1 over 1. It would be another coefficient over coefficient situation. And so that limit would be 1. 1 is positive and finite, so that's good. So far, we know that if p is 1/2, this thing diverges. If p is 1, this thing diverges. I'm sorry, if p is 1/2, this thing diverges. If p is less than 1/2, this thing diverges. All right. So the only other thing to consider is if this exponent is greater than 1. So let's do that. So let's let 2p be greater than 1, which of course would mean that p is greater than 1/2. And so the limit as n approaches infinity of n over n raised to some number that's bigger than 1 plus n. All right. Well, now this thing is bottom heavy, as you would have called it in Math 3. And so that means that this limit itself is going to 0. This limit is 0. This expression is headed to 0 as n approaches infinity. Well, 0 is not positive. And so this answer is no good for our purposes. So our answer is, for this thing to diverge, p can be equal to 1/2 or p can be less than 1/2. So our answer is p is less than or equal to 1/2. That's it.